Hello friends, welcome to this video lectures on experimental stress analysis. So today we'll discuss once again based on the chapter number 6, that is strain measurement. In the last three lectures we have discussed about the electrical resistance strain gauge. In that we have discussed about the basic construction working principle. Then in the part 2 we have discussed about the basic classification of the strain gauges. Then we have discussed about the different configurations of the Wheatstone bridge circuit. For that purpose, we have discussed about the basic construction and working principle of Wheatstone bridge circuit. And then we have derived one small formula for the Wheatstone bridge circuit. So in the last two lectures, that is in the part number 2 and in part number 3, we have discussed about the four configurations of the Wheatstone bridge circuit. So in that configurations, we have discussed about the single arm sensitive bridge circuit. Then we have discussed about the two arm sensitive bridge circuit. In that two arm, again we have discussed about the two important configurations, that is the two arm sensitive bridge circuit when it is subjected to the same in magnitude, same in nature, and the two arm sensitive bridge circuit when it is subjected to the same in magnitude and opposite in nature. So for these two derivations, we have derived the formula, that is output of Wheatstone bridge circuit. And then at the last we have discussed about the four arm sensitive bridge circuit. But whatever the four configurations we have discussed in the part 2 and part 3 of this particular chapter, in that one assumptions we have considered, that is whatever the strain gauges are used in single arm sensitive bridge circuit, in two arm sensitive bridge circuit, and in four arm sensitive bridge circuit, all the strain gauges are considered as a linear strain gauges. Why it is called as a linear strain gauges? Because if the force is applied in any particular direction, whatever the strain is induced in that particular direction, that strain is called as a linear strain. So whatever the four configurations we have discussed in the last two lectures, in that for all the configurations, all the strain gauges are subjected to the linear strain gauges, because all the strain gauges are pasted in the direction of force. But there are so many applications are there in which the force is applied in one direction and the force is applied in another direction. For example, let us take a simple example of cantilever beam. In case of a cantilever beam, if the force is applied in x direction, at that time, due to that force applied in x direction, the strain is developed in the x direction, as well as some amount of strain is also developed in the y direction. But there is no force in y direction, so whatever the strain is induced in y direction, that strain is called as a lateral strain. And whatever the strain induced in the direction of force or in x direction, that strain is called as a linear strain. But in many of applications, sometimes we have to measure both the quantities. That means we have to measure the linear strain as well as we have to measure the lateral strain. So if I have to measure such types of the strains simultaneously, so my requirement is that I have to provide linear strain gauges as well as lateral strain gauges in the application. So in this particular part 4 of this particular chapter, we are going to discuss about the same configurations of the Wheatstone bridge circuit. So in the last two lectures also we have discussed about the two arm sensitive bridge circuit and the four arm sensitive bridge circuit. But in this chapter, once again we are discussing about the two arm sensitive bridge circuit. But in that two arm sensitive bridge circuit, whatever the two strain gauges are there, that two strain gauges are not a linear strain gauges, but out of that, one strain gauge will be considered as a linear strain gauge and another strain gauge is considered as a lateral strain gauge. Similarly, the four arm sensitive bridge circuit also we have discussed in the last lecture. But in that last lecture, whatever the four arm sensitive bridge circuit we have considered, in that all the four strain gauges are subjected to the linear strain gauges. But now in this particular chapter, once again we are discussing about the output of the four arm sensitive bridge circuit, in which out of the four strain gauges, two strain gauges are subjected to the linear strain gauges and remaining two strain gauges are subjected to the lateral strain gauges. So for this particular two derivations, once again I have to derive the output formula for the Wheatstone bridge circuits, and I have to check if the linear strain gauges and the lateral strain gauges are used in any application, how the output of that bridge circuit it will get changed. So that detailed derivations we are going to discuss in this particular chapter. Then we'll discuss about the new point, that is transverse sensitivity and the cross sensitivity. So this is one a constant factor, that is transverse sensitivity, which is also called as a cross sensitivity. This factor we have to introduce in the strain gauge application if the almost accuracy is required. So the basic definition related to this, then basic concept related to the transverse and cross sensitivity we are going to discuss in this lecture. Also we are going to derive a small derivation for the transverse sensitivity or the cross sensitivity, and also we are going to derive a small derivation to find out the error during the meter reading, because what happens sometimes due to the many of problems, some errors are introduced in the meter reading, and if we have to consider or if we have to achieve the almost accuracy or almost sensitivity, at that time whatever the error is induced during the measurement, that error also we have to consider in order to achieve the almost sensitivity. So that concept also we are going to discuss in the transverse and the cross sensitivity. So now we'll start with the two arm sensitive bridge circuit with one linear and one lateral strain gauge. So already I have explained why this particular circuit is called as a two arm sensitive bridge circuit, because in Wheatstone bridge circuit it consists of a total four arms. Out of these four arms, only two arms are sensitive because only two strain gauges are mounted on the Wheatstone bridge circuit. That is, the strain gauge 1 is mounted on the first arm, that is arm AB, and the strain gauge 2 is mounted on the second arm, that is arm BC. But out of the two strain gauges, both strain gauges are not a linear strain gauges, or both gauges are not a lateral strain gauges. Out of the two strain gauge, one strain gauge, that is strain gauge number 1, which is mounted on the arm number 1, it will be considered as a linear strain gauge, and the strain gauge 2, which is mounted on the arm number 2, will be considered as a lateral strain gauges. Therefore, this particular circuit is called as a two arm sensitive bridge circuit with one linear and one lateral strain gauge. So same circuit diagram is explained with the help of this particular application, which consists of one cantilever beam. In that cantilever beam, the one strain gauge 1 is pasted at the top side, and the strain gauge 2 which is pasted at the bottom side, and whatever the strain gauge is pasted at the top of cantilever beam will be considered as a linear strain gauge, because the strain gauge 1 is pasted in the direction of force, but whatever the strain gauge 2 is pasted at the bottom side, it is not pasted in the direction of force. Therefore, this particular strain gauge is called as a lateral strain gauges. If such types of the lateral strain gauges are introduced in Wheatstone bridge circuit, then the output of that particular bridge circuit will get changed as compared to the output of Wheatstone bridge circuit consist of linear strain gauges. Because in the Wheatstone bridge circuit, if all the strain gauges are considered as a linear strain gauge, so their output is obtained only in the form of K into epsilon term. But in the same bridge circuit, if one or more than one lateral strain gauges are introduced, then that output of that particular bridge circuit is obtained in the form of mu, because wherever we are introducing this particular lateral concept, in such applications we have to introduce the mu, because as we know that the simple example is there, if the linear strain gauge or linear strain is given to you, and if we have to calculate the lateral strain, but to calculate the lateral strain, initially the linear strain will be given, and along with that linear strain one constant parameter is also given, that is mu. And as we know that the simple formula is there, lateral strain is equal to mu into linear strain. That means by using the value of linear strain and by using the value of mu, that is Poisson's ratio, I can calculate the lateral strain. Therefore, that particular mu factor plays very important role during the lateral strain calculations. So now now I have to derive the output of this particular two arm sensitive bridge circuit, in which one linear and one lateral strain gauge is there. So if I will go through this particular circuit diagram once again, so I have to calculate the value of R1, that is resistance of strain gauge number 1. Similarly, I have to calculate the value of strain gauge 2, that is R2. That R3 and R4 are the fixed resistor, therefore their resistance value becomes constant before application of load as well as after application of load. Now initially I will calculate the R1, that is the value of linear strain gauge. So R1 is equal to R plus delta R. So this capital R represents the resistance of strain gauge before application of load. Then this delta R represents the resistance of strain gauge after application of load. That means change in resistance which is taking place after application of load. And this plus sign represents the tension of the strain gauge 1 is taking place, because if you go through this particular cantilever beam, the strain gauge 1 is pasted at the top side and the top portion of the cantilever beam is subjected to tension. Therefore here I have taken plus sign as an addition of both resistance. Then I have to calculate the value of R2. Then value of R2 is equal to R. Once again, this capital R represents the resistance of strain gauge before application of load. Then this mu into delta R, in that this delta R represents the change in resistance after the application of load, and this negative sign represents the compression of the strain gauge is taking place. Because if you go through the cantilever beam, once again the strain gauge 2 is pasted at the bottom side, and the bottom portion of the cantilever beam is subjected to the compression. Therefore the compression of the strain gauge is taking place, means the resistance is decreases from R to delta R. Therefore here the minus sign is taking place. But in addition to that, whatever the change in resistance we have calculated from the strain gauge 2, for that change in resistance I have to multiply by mu, because the second strain gauge is subjected to the lateral strain gauge, or it is subjected to the lateral strain. Therefore wherever the strain gauges are pasted in Wheatstone bridge circuit, I have to check whether that strain gauge is linear strain gauge or that strain gauge is lateral strain gauge. If linear strain gauge is there, need not require to multiply by mu to the change in resistance. But if any lateral strain gauge is provided in the bridge circuit, so in that particular condition we have to multiply by mu to the change in resistance wherever such types of the lateral strain gauges are pasted in the bridge circuit. Therefore the value of R2 becomes R2 is equal to R minus mu into delta R. Means this negative sign represents the compression, and this mu represents this particular strain gauge 2 is subjected to the lateral strain or the lateral strain gauges. Therefore here I have multiplied by mu to the change in resistance. So this is the basic difference between the value of R1 and R2. But remaining two resistors, that is R3 and R4, are the fixed resistor. Their value remains constant before load, application of load. Therefore R3 is equal to R4 is equal to capital R. And then I have to put these particular values in the above E0 equation to calculate the output of this particular bridge circuit. So if I will put the values, that is R1 is equal to R plus delta R, so your equation becomes E0 is equal to ES in bracket. So instead of R1 I have to put R plus delta R, then at the denominator R1 plus R2, so R1 is equal to R plus delta R, this plus sign as it is. Value of R2 I have calculated from the bridge circuit, that is R minus mu into delta R, because this is the lateral strain gauge. So put the value of R2, that is R minus mu into delta R, this minus sign as it is. Instead of R3 and R4 I have to take the value of R. Therefore at the numerator only R is present, at the denominator R3 plus R4, that means R plus R. This equation becomes denominator at the 2R. Then I have to go for the simplification, that is E0 is equal to ES in bracket, that numerator terms R plus delta R as it is. So here if I will go to this particular denominator side, so here plus R is there, so here plus 2R, this delta R remains as it is, minus mu into delta R as it is, this minus sign is also as it is, this R from the numerator and denominator it will get cancelled, only remaining 1 upon 2. But if you go through the denominator of this particular two equations, the denominators are not same. So in the next step what I have to do, I have to make the denominator same by making the cross multiplication. So this R plus delta R I have to multiply by mu, and this 2R plus delta R minus mu into delta R I have to multiply by 1. So to make the denominator same, the next step is equal to E0 is equal to ES in bracket, by making the cross multiplication 2 into R plus 2 delta R, so 2 into R plus 2 into delta R, this minus sign is as it is. So for this particular term if I will multiply by 1, so this minus 2R as it is, then this minus sign if I will give inside the bracket, so here it becomes minus delta, this minus and this minus it becomes plus, therefore plus mu into delta r. And for making the denominator same, we have to make the multiplication of this particular both the denominator terms, that is the equation becomes 2 into 2r 4r plus delta r into 2 delta r minus mu into delta r into 2, that is minus 2 mu delta r. So the next step, by cancelling the sum of the values, that is E0 is equal to Es in bracket. So from the numerator, if you go through it, here plus 2r is there, minus 2r is there, it will get cancelled. Here plus 2 delta r minus delta r, only delta r is remaining, and this plus mu into delta r is as it is. So I will write this plus mu into delta r as it is, plus delta r denominator terms are as it is. Now the next step is equal to E0 is equal to Es in bracket. So in the numerator, here delta r is present, here also delta r is present. If I will take outside the bracket, so only terms becomes 1 plus mu divided by denominator terms are as it is. So this is the equation by making the denominator same, by cancelling the value with each other. Now once again I have to write the equation, that is final equation or the final output of that particular bridge circuit in the form of k into epsilon. But here in order to obtain the value in the form of k into epsilon, this delta r upon r, this term should be present in the equation. So what I have to do, once again I have to divide by capital R to both numerator and the denominator. So once again E0 is equal to Es in bracket. So at the numerator divide by R, that is delta R upon R in bracket 1 plus mu. Similarly I have to divide by this particular capital R to the denominator. So equation becomes 4r upon r plus 2 delta r upon r minus 2 mu delta r upon r. Then as we know that this delta r upon r is equal to k into epsilon, so the next step or next equation becomes E0 is equal to Es in bracket. From this delta r to r I have written the k into epsilon in bracket 1 plus mu. So from the denominator, this r it will get cancelled, only 4 is remaining. Again plus 2 into delta r upon r, and as we know that delta r upon r means k into epsilon, so the next step becomes 2 into k into epsilon, this minus sign as it is, once again this 2 into mu as it is, and once again delta r upon r is equal to k into epsilon. That means at the numerator also k into epsilon is present, as well as at the denominator also k into epsilon term is present. So but as we know that whatever the k into epsilon terms are present at the denominator, we have to neglect all the k into epsilon terms from the denominator along with their multiplying factor. So here at the denominator 2 times k into epsilon is present, so by neglecting this k into epsilon from the denominator, I will get the final equation E0 is equal to Es in bracket k into epsilon in bracket 1 plus mu divided by 4. And this is the output of Wheatstone bridge circuit for the 2 arm sensitive bridge circuit, in which one linear strain gauge is there and one lateral strain gauge is there. So if I will compare this particular output with the 2 arm sensitive bridge circuit in which both the strain gauges are linear, so output of that particular 2 arm sensitive bridge circuit is E0 is equal to Es in bracket k into epsilon divided by 2. But here the output is obtained in the form of mu, as well as this particular dividing factor is also get changed. That means in bridge circuit or in any application, if I will introduce any lateral strain gauge, at that time output of that particular bridge circuit it will get changed, and therefore there is a difference between the 2 arm sensitive bridge circuit in which both are the linear strain gauges, and there is a difference between the 2 arm sensitive bridge circuit in which out of the 2 strain gauges, one is a lateral strain gauge and another is a linear strain gauge. So this is the output we have derived for the 2 arm sensitive bridge circuit, in which it consists of a one linear strain gauge and one lateral strain gauge. So this is about the 2 arm sensitive bridge circuit. Now we'll discuss about the 4 arm sensitive bridge circuit, in which out of the 4 strain gauges, the 2 strain gauges are subjected to the linear strain gauges and the remaining 2 are subjected to the lateral strain gauges. For the same condition, that is 4 arm sensitive bridge circuit, we have derived the derivation in the last lecture. But in the last lecture, whatever the forearm sensitivity circuit we have considered, in that all the 4 strain gauges are the linear strain gauges. But now in this particular condition, out of 4 strain gauges, 2 are the linear strain gauges and remaining 2 are the lateral strain gauges. So if you go through this particular figure, the circuit diagram consists of a 4 strain gauges. Out of the 4, the strain gauge number 1 and the strain gauge number 2, strain gauge number 1 and the strain gauge number 4 are in front of each other, and these 2 strain gauges are subjected to the linear strain gauges, and the strain gauge 2 and strain gauge 3 are in front of each other, and this strain gauge 2 and the strain gauge 3 are subjected to the lateral strain gauges. In addition to that, the strain gauge 1 and the strain gauge 4 are subjected to the tension, which is represented by this particular cantilever beam, while the strain gauge 2 and the strain gauge 3 are subjected to the compression, which is also indicated by this particular cantilever beam. So once again, as the 2 linear strain gauges are there and the 2 lateral strain gauges are there, I have to calculate the value of R1, R2, R3 and R4, and that value I have to put in the E0 equation to calculate the output of this particular bridge circuit. So how the values are calculated? As we know that the strain gauge 1 and the strain gauge 4 are subjected to the tension and both are subjected to the linear strain gauges. Therefore, the value of R1 is equal to R4 is equal to R plus delta R. Once again, this R, capital R, represents the resistance of strain gauge before application of load. Delta R represents the resistance of strain gauge, that is change in resistance after the application of load. And this plus sign represents both the strain gauges are subjected to the tension as well as both are subjected to the linear strain gauges. But what about remaining 2, that is strain gauge 2 and 3 are subjected to the lateral as well as they are subjected to the compression. Therefore, R2 is equal to R3 is equal to R minus mu into delta R. This minus sign indicates both the strain gauges are subjected to the compression, and this mu represents the strain gauge 2 and strain gauge 3 are subjected to the lateral strain gauges. Therefore, whatever the change in resistance value I have calculated, to this change in resistance value I have to multiply it by mu, because these 2 strain gauges are subjected to the lateral strain gauges, and whatever the strain gauge 1 and 4 are there, these are subjected to the linear strain gauges. Therefore, need not required to multiply it by mu to this change in resistance. So this value of R1 to R4 I have calculated. Now I have to put all these values in the E0 equations. If I will put the value of R1 at the numerator, that is R plus delta R, then once again R plus delta R plus R2 value R minus mu into delta R, this minus sign as it is. Once again, value of R3 is equal to R minus mu into delta R, at the numerator I have written. Then R3 plus R4, again the value of R3 R minus mu into delta R, this plus sign as it is. Value of R4 R plus delta R, bracket complete. Then next step, E0 is equal to ES in bracket. So this numerator as it is R plus delta R, but the denominator, this R plus this R, 2R plus this delta R as it is, minus mu into delta R as it is. This minus sign is as it is. Again R minus mu into delta R, this numerator term I have written as it is. Again from the denominator, this R plus R, 2R plus delta R as it is, minus mu into delta R as it is. If I will compare this both the equations, this 2R plus delta R minus mu into delta R, similarly 2R plus delta R minus mu into delta R, the denominators are already same, so need not require to make the denominator same by making the cross multiplication. So by keeping the denominator same, I will write the next step, E0 is equal to ES in bracket. Denominators are already same, therefore 2R plus delta R minus mu into delta R, but at the numerator also we have to take the subtraction. Therefore R plus delta R as it is, this minus sign as it is. If this minus I will give inside the bracket, so here minus R as it is, this minus and this minus, it becomes plus, therefore plus mu into delta R. Then next step, this plus R minus R, it will get cancelled. Only equation becomes E0 is equal to ES in bracket delta R plus mu into delta R divided by 2r plus delta r minus mu into delta, this denominator terms I have written as it is, bracket complete, is equal to. So at the numerator delta r is present, so if I will take delta r outside the bracket, so equation becomes es in bracket delta r in bracket 1 plus mu divided by this denominator as it is, that is 2r plus delta r minus mu into delta r. Now you will get the equation in the form of delta r, but I have to write this E0 equation in the form of k into epsilon, and to obtain this particular k into epsilon term in the equations, I have to generate the equation in the form of delta r upon r. So once again I have to divide by capital R to both numerator and the denominator. So by dividing this capital R to the numerator, equation becomes E0 is equal to Es in bracket. So at the numerator this delta r upon r 1 plus mu as it is, at the denominators also this 2r upon r plus delta r upon r minus mu into delta r upon r is equal to, and as we know that delta r upon r is equal to k into epsilon, so I will write the equation in the form of k into epsilon, that is E0 is equal to Es in bracket k into epsilon in bracket this 1 plus mu as it is. At the denominator this r it will get cancelled, only 2 is remaining. Here delta r upon r k into epsilon I have written as it is, this minus sign as it is, this mu is also written as it is, and again this delta r upon r is equal to k into epsilon. So at the numerator also as well as at the denominator also k into epsilon terms are present, but as we know that whatever the k into epsilon terms are present at the denominator, we have to neglect it, and I have to write the final equation by neglecting all the k into epsilon terms from the denominator. The final equation becomes E0 is equal to Es in bracket k into epsilon in bracket 1 plus mu divided by 2. And once again in the forearm sensitive bridge circuit, as the two linear strain gauges and the two lateral strain gauges are there, due to that lateral strain gauges the output is obtained in the form of 1 plus mu, or it is obtained in the form of mu parameter. So this is the output of forearm sensitive bridge circuit in which the two linear strain gauges are there and the two lateral strain gauges are there. But if I will compare this particular output with the two arm sensitive bridge circuit in which one linear strain gauge is there and one lateral strain gauge is there, and after the comparison it has been observed that the output of two arm sensitive bridge circuit in which one linear and one lateral strain gauge is there, that output is equal to Es in bracket k into epsilon in bracket 1 plus mu divided by 4. For the two arm sensitive bridge circuit the dividing factor is 4, but for the forearm sensitive bridge circuit the dividing factor is 2. Therefore the output of forearm sensitive bridge circuit in which two linear and two lateral strain gauges are there, and this output is 2 times greater than two arm sensitive bridge circuit in which one linear and one lateral strain gauge is there. Therefore once again if we are increasing the number of lateral strain gauges in any bridge circuit, once again output is also increases. That means from this particular configurations we can say that the strain gauges may be linear strain gauges or strain gauges may be lateral strain gauges, but if we are increasing the number of linear strain gauges or if we are increasing the number of lateral strain gauges, the output is also increases. But if only linear strain gauges are present in the bridge circuit, the mu term is not introduced in the output. But if any lateral strain gauge is present in any bridge circuit, the output is obtained in the form of mu parameter, or it is obtained in the form of 1 plus mu, and this related to this lateral strain gauges. Today we have derived the two derivations for the two arm sensitive bridge circuit as well as four arm sensitive bridge circuit. So this is about the configurations of the Wheatstone bridge circuit in which lateral strain gauges are introduced. So like that we have discussed about the total 8 configurations for the Wheatstone bridge circuit, that is for the single arm sensitive bridge circuit, two arm sensitive bridge circuit, as well as forearm sensitive bridge circuit. In that also we have discussed the derivations for all the linear strain gauges. Also we have discussed about the derivations for the lateral strain gauges. So this is about the different configurations of the Wheatstone bridge circuit. Now we'll discuss about the next point, that is transverse and the cross sensitivity. Now, why this transverse sensitivity and the cross sensitivity is introduced in the strain gauge application? Because there is one reason. Because when the strain gauge is subjected to the loading, as it is subjected to the loading, its resistance will get changed. But sometimes whatever the strain gauge is pasted, sometimes the strain gauges are pasted in the direction of force. For example, if I will take the example, that is, let us consider this is a one foil type of strain gauges, that is foil is provided in this particular foil type of strain gauges. So the force is applied in x direction. So if the force is applied in x direction, the some amount of strain is also induced in x direction, which is represented by this particular epsilon x. But whatever the force is applied in x direction, that force will be considered as a tensile force. Therefore, whatever the strain is induced in this particular x direction, that strain is also considered as a tensile strain. But as the force is applied in x direction, the strain is also developed in the x direction, which is represented by the epsilon x. But at the same time, some amount of strain is also developed in the direction of y. So this epsilon y represents the compressive strain induced in this particular strain gauge, and it is also represented in the opposite directions, that is the force applied in x direction will be considered as a tensile strain, but the whatever the strain is induced in the y direction, that strain will be considered as a compressive strain. But and instead of that, whatever the strain induced in the y direction, that strain is called as a transverse strain, or it is considered as a transverse direction or the transverse sensitivity. But as we have to calculate the value of epsilon x, but sometimes while calculating this particular value of epsilon x, whatever the strain induced in the transverse direction or in the direction of y, that epsilon y creates the error during the measurement. My requirement is that only I have to calculate the epsilon x, but while calculating that particular epsilon x value, this epsilon y creates the error during measurement. And if almost sensitivity is required, I have to consider this particular error value. If the sensitivity is not required, neglect that particular error which is produced due to that particular epsilon y. Why it is happening? Because if I will take the example, if the force is applied in the x direction, the extension of this particular foil is taking place, therefore this epsilon x are moving outwards. But at the same time, due to the force applied in x direction, the compression of the foil is taking place in y direction or in the transverse direction. Therefore, these epsilon y's are represented in the form of compressive manner. But this epsilon y creates the error during the measurement. But as already I have explained, if almost accuracy is required while taking the reading, at that time this error also we have to consider during the measurement. So if I have to consider this particular error, so I have to introduce this particular transverse sensitivity or the cross sensitivity factor in the strain gauge applications. Therefore, the definition of the transverse sensitivity, that is, it is defined as the gauge factor along transverse direction to the gauge factor along axial direction. So this particular x direction will be considered as a axial direction, and this y direction will be considered as a transverse direction. And according to that axial and according to that transverse direction, the definition of gauge factor has been defined, that is, it is defined as the ratio of gauge factor along transverse direction, means in y direction, to the gauge factor along axial directions, mean x direction, and this transverse sensitivity is indicated by st, which is equal to kt upon ka. What is meant by this particular k? K is called as a gauge factor, but here I have written KT, means gauge factor along transverse direction to the gauge factor along the axial direction. So this is the equation number 1 which we have obtained by the definition of the transverse sensitivity or the cross sensitivity. But as we know that the definition of the gauge factor, what is the definition of gauge factor? That is, gauge factor is defined as the ratio of change in resistance upon original resistance to the change in length upon original length. But at the denominator, whatever the change in length upon original length is there, that formula we have replaced in the form of strain, because the definition of the strain is change in dimensions upon original dimensions or change in length upon original length. Therefore, we have written the equation for the gauge factor K is equal to delta R upon R divided by epsilon. But here the gauge factor is present in transverse direction as well as gauge factor is present in axial directions, means gauge factor is present in the direction of Y as well as the gauge factor is present in the direction of X. Therefore, this gauge factor I have written in transverse direction as well as in the axial direction. Therefore, Kt is equal to delta Ry upon R divided by epsilon Y, means change in resistance upon original resistance divided by strain. But Kt is subjected to the Y direction, therefore change in resistance taking place in Y direction divided by original resistance divided by strain induced in Y direction. This is the equation number 2. Then Ka represents the gauge factor in axial direction or the gauge factor in the direction of X. Therefore, delta Rx upon R divided by epsilon X, means the change in resistance in X direction to original resistance divided by strain induced in the X direction. So this is the equation number 3, and from equation 2 and from equation number 3, by rearranging the terms, I have written the equation 4, that is, I have written the equation in the form of delta Ry upon R by taking this particular epsilon Y to the left side. Similarly, I have written the equation delta Rx upon R by taking this particular epsilon X to the left side. Therefore, I will get the equation 4 and 5, that is delta Rx upon R is equal to Ka into epsilon X. Similarly, delta Ry upon R is equal to Kt into epsilon Y. So this is the equation number 4 and equation number 5, which is obtained from equation 2 and 3 by rearranging the terms. But as we know that the total change in resistance, so some amount of resistance will get changed in X direction, some amount of resistance is also get changed in Y direction, means in only two directions the resistance will get changed, and that total change in resistance is equal to change in resistance in X direction, that is delta Rx, plus change in resistance in Y directions, that is delta Ry. Therefore, total change in resistance is indicated by delta R is equal to delta Rx plus delta Ry. But as I have to write the equation in the form of gauge factor, so what I have to do, whatever this particular change in resistance value is there, so to this particular equations I have to divide by capital R. So if I will divide this particular capital R to this above equation, so this delta R upon R is equal to delta Rx upon R plus delta Ry upon R, and as we know that this delta R upon R I have to keep as it is. And from equation number 4, as we know that delta Rx upon R means Ka into epsilon X, so from equation number 4 I have written Ka into epsilon X. From equation number 5, as we know that delta Ry upon R is equal to Kt into epsilon Y, so instead of this delta Ry upon R I have written Kt into epsilon Y. So this is the terms or this particular equation I have written from the equation number 4 and from the equation number 5. The next step is this delta R upon R is as it is equal to Ka into epsilon X, Kt into epsilon Y. So from this particular equation, if I will take this Ka into epsilon X as a constant term, so if I will take this particular Ka into epsilon X outside the bracket, so equation becomes Ka into epsilon X in bracket, only one is present because from this term I have taken this Ka into epsilon X as a common, plus, but to this particular side this Ka and epsilon X is not present. As they are not present to this particular side, so I have to divide by Ka and I have to divide by epsilon X. So the equation becomes Ka into epsilon X in bracket 1 plus Kt upon Ka because Ka is not present into epsilon Y upon epsilon X because epsilon X is also not present. And the next step I have written this delta R upon R as it is equal to Ka into epsilon X as it is in bracket 1 plus. from the equation number 1, as we know that the definition of the transverse sensitivity or the cross sensitivity, that is St is equal to Kt upon Ka, and this term Kt upon Ka I have replaced in the form of St. Therefore, instead of this Kt upon Ka, I have written this St, which represents the transverse sensitivity and the cross sensitivity, multiply by epsilon y upon epsilon x as it is. Then, as we know that the basic formula for the mu, that is Poisson's ratio, is equal to minus lateral strain upon linear strain. And in the above figure, as we know that in x direction, whatever strain is induced, that strain is called as a linear strain because the force is applied in the direction of x. But whatever the strain is induced in this particular y direction, that strain is called as a lateral strain because the force is not applied in y direction, force is applied in x direction. Therefore, as per the definition of mu is equal to minus lateral strain upon linear strain, and from the figure the lateral strain will be considered as epsilon y, this minus sign as it is, the lateral strain will be considered as epsilon y and the linear strain will be considered as epsilon x because force is applied in the x direction, no force is applied in y direction. And as we know that minus epsilon y upon epsilon x is equal to minus lateral strain upon linear strain is equal to mu. Therefore, instead of that minus epsilon y upon epsilon x is equal to minus mu. Therefore, in the above equation, if I will put the value of epsilon y is equal to epsilon x as a mu, but here minus epsilon y upon epsilon x is equal to minus mu. Therefore, here also I have to put this particular mu value in the negative manner, and I will get the next equation, that is delta r upon r is equal to this Ka into epsilon x as it is in bracket 1 minus mu into St, because epsilon y upon epsilon x is equal to mu, but here epsilon y is present in the negative manner. Therefore, you will get the mu in the form of negative, and this minus mu I have to put in this particular equation, and I will get the value in the form of mu, that is delta r upon r is equal to Ka into epsilon x in bracket 1 minus mu into St. And by keeping this particular mu is equal to 0.285, I will write the final equation, that is delta r upon r is equal to Ka into epsilon x in bracket 1 minus 0.285 into St, and this is the final output of the transverse sensitivity. And this particular effect we have to consider, or this transverse sensitivity we have to consider if the almost accuracy is required. That means if we are calculating this particular change in resistance value in the strain gauge applications, while calculating this particular change in resistance value, if almost accuracy is required, at that time we have to consider this particular transverse sensitivity, or we have to consider this particular formula to calculate the change in resistance. But if almost accuracy is not required, need not require to consider this particular transverse sensitivity factor or cross sensitivity factor in the strain gauge application. So this is about the detailed derivation of the transverse sensitivity, which is also called as a cross sensitivity. And now whatever the error we have to calculate, whatever the error will be introduced, that error also I have to consider, and how that particular error is calculated. So for that particular error calculation, simple definition is there, that is error is defined as the ratio of difference between meter reading and epsilon x to the epsilon x. Means in the mathematical form, the small e represents the error, which is equal to epsilon m minus epsilon x. That epsilon m means meter reading which is obtained from the display, minus epsilon x means strain induced in x direction, divided by epsilon x, again the strain induced in x direction. And whatever the meter reading we have to calculate, that meter reading can calculate by using this particular equation, that is epsilon m is equal to epsilon x in bracket 1 minus mu into St divided by 1 minus 0.285 into St. And by putting this particular epsilon m in the meter reading, I can derive the small equation for calculating the errors, that is E is equal to, by putting this particular epsilon m in this particular error equation, so I will get the equation, that is E is equal to epsilon x in bracket 1 minus mu into st divided by 1 minus 0.285 into st minus this epsilon x I have written as it is. At the denominator also epsilon x is present, I have written as it is. Now if you go through the numerator, here epsilon x is present, here epsilon x is present. If I will take outside the bracket, the error equation becomes E is equal to epsilon x outside the bracket in bracket 1 minus mu into st divided by 1 minus 0.285 into st minus 1, because epsilon x I have taken outside the bracket. This denominator epsilon x as it is I have written at the denominator. Then from this particular above equation, at a numerator also epsilon x is present, at the denominators also epsilon x is present. So this epsilon x, it will get cancelled. Only equation for the error E is equal to 1 minus mu into st divided by 1 minus 0.285 into st. This minus 1 I have written as it is. Now here the denominators are not same, so by making the denominators same, by making the cross multiplication, so my equation becomes this 1 minus mu into st is as it is, minus by making this particular cross multiplication, if this minus sign I will give inside the bracket, so here it becomes plus, therefore 1 plus 0.285 into st, and the denominators are same, that is 1 minus 0.285 into st, and at the denominator this plus 1 minus 1 it will get cancelled, and final equation will be written for the error by taking these positive terms first and negative terms afterwards. The equation becomes error is equal to 0.285 into st, which is positive, minus mu into st, which is negative, divided by this denominator is as it is, that is 1 minus 0.285 in st. I have written denominator as it, and this is the final equation to calculate the error which is introduced while taking the readings. And this particular error value I have to calculate if the almost accuracy or the almost sensitivity is required in the strain gauge application. If the sensitivity and the accuracy is not required, then this error need not required to calculate, but if the accuracy and the sensitivity is required, by using this particular formula I can calculate that particular error, and that error value I can subtract from the final output equation. And if this error will be subtracted or if it will be considered while taking the final readings, while considering this particular error value, whatever the final output we have calculated, that output becomes more sensitive, and that error will be calculated by using this particular simple formula. So this is about the concept of transverse sensitivity and the cross sensitivity. In the first phase we have derived the small derivation to calculate the change in resistance in the form of transverse sensitivity, and why this transverse sensitivity and the cross sensitivity factor we have to consider in the strain gauge applications. So that detailed explanation and detailed derivations we have discussed in the first part, and whatever the error we have to calculate, for that error calculation also we have derived even small formula, and from that particular small formula I can calculate the error induced in the meter readings or the error induced in the strain gauge application. So this is about the transverse sensitivity and the cross sensitivity which we have to consider in the strain gauge applications. So this is about the part 4 of this particular chapter number 6, in which we have discussed about the remaining two configurations of the Wheatstone bridge circuit, that is two arm sensitive bridge circuit in which one linear and one lateral strain gauge is there, and then we have discussed about the forearm sensitive bridge circuit in which two linear and two lateral strain gauges are there, and then we have discussed about the concept of transverse sensitivity and the cross sensitivity in which we have derived a small derivation for the transverse or the cross sensitivity factor, and then we have derived a small derivation to calculate the error. So this is about the chapter number 6 related to the configurations and the transverse sensitivity. Thank you.